day, everyone. Welcome to the second edition of CosmoPalooza. So this morning, we're very happy to welcome HSC as our first collaboration update for the series that's going to take place over 4 days. We will now leave the floor to the HSC collaboration for 1 hour to tell us about the exciting developments that's taken place with them. So if you guys want to turn on your cameras and start sharing your screen.
You. Screen share link working?
Yes.
Okay, great. Hello, everyone. So this is Sugiyama, a postdoc from University of Pennsylvania, and for thanking for having us. And this is really great opportunity to have a present latest update for weak ranging cosmology HCC year 3 result. So we will talk about the latest result of the weak ranging HCC result. So before that, I will mainly talk about general overview of the weak ranging and the Subaru HCC. So we are studying the observation cosmology. Within that, we are now reaching the standard cosmological paradigm, in which we have the lambda CDM model, which is composed of the cosmological constant lambda, which explains the accelerating expansion of the universe. And also, universe is composed of cold dark matter, which is called CDM, and which drives the growth of the large scale structure, especially in late time universe. This late time universe is also considered to originate from the inflation, and which eventually formed the large scale structure we observe in late time universe. And also, the recent observation, for example, cosmological anisotropy of the cosmic microwave background and accelerating expansion by supernovae, and the observation of the galaxy clustering. For this observation, lambda CDM model will explain these observational results. And using this observational result or data, we are now reaching the era of the precision cosmology, in which we can determine the cosmological parameter at the percent level, like cosmological abundance of the cosmological parameter and cold dark matter, or amplitude of the large scale structure in the daytime universe. So with this precision cosmology, we are now finding the possible tension in SH parameter. So here I'm showing the parameter estimation obtained from the early time universe and late time universe on the right-hand side. Especially, we are now focusing on the SH parameter. So this is a combination of the two cosmological parameters. First one is sigma 8, which characterizes the clumpiness of the cosmic structure, large scale structure today. And the omega matter is energy density of the matter today. And it is well known that weak ranging data is constrained this combination, SH parameter best. So we are now focusing on this SH parameter. And you can see that there is a discrepancy between the late time universe, which is shown above dashed line, and large scale structure result below a dashed line. And this is so-called SH tension. And if this SH tension is real, this basically indicates that the breakdown of the lambda CDM model. So we are now keen to testing the lambda CDM model via this SH tension, especially working on a more larger data set of the weak ranging or the late time universe surveys. So to do so, we are mainly focusing on the gravitational weak ranging effect, which is effect of the distortion of the distant galaxy. So light is emitted from the distant galaxy, and this light, the path of light, is basically due to the foreground, the gravitational lensing effect caused by the foreground large scale structure. The shape of the distant galaxy is distorted, and this distortion is so-called the shear, and this shear is characterized by this equation. and integration over the line of sight of the matter density contrast. And with easy calculation, we can see that this shear is very sensitive to this cosmological parameter, omega matter and sigma 8. So this is the reason why we can constrain these cosmological parameter from the weak ranging observation. However, this weak ranging is pretty literally weak ranging effect, weak effect. So what we observe is shown in bottom right panel. So what we observe in the weak ranging galaxy shape is the sum of the intrinsic galaxy shape and the weak ranging effect. And this weak ranging effect is very, very small compared to the intrinsic shape. So if we only focus on a single galaxy shape, we cannot infer the cosmological parameter, or we cannot infer the weak ranging effect at all. However, if we analyze many number of galaxies at the same time, we can extract the weak ranging effect from the coherent pattern of the weak ranging effect. So this is what we do in weak ranging analysis. Especially for the statistical analysis, we are going to use a two-point correlation function. So first two-point correlation function is a cosmic shear, which is an autocorrelation function of the weak ranging shear. I mean the shear shape of the galaxy, observed galaxy. And the second observable is galaxy ranging. It is a cross correlation of the galaxy and the weak ranging shear. And it is known that this cross correlation, I mean the galaxy ranging, cannot constrain the cosmological parameter with its own probes. So we needed to combine the galaxy clustering with galaxy ranging. So this is a so-called 2x2 point analysis. And the last observable is the cluster ranging, which is a cross correlation of the cluster position and weak ranging shear. So we will talk about the cosmology analysis using these observable later. So to do this analysis, we use Subaru Suprime-Cam HSC instrument. So Subaru has a very wide field of view, 1.5 degree diameter. And thanks to the very huge primary mirror of the Subaru telescope, it has a huge light collecting power, and which enable us to observe the faint object or the distant galaxies. And also the HSC installed on the prime focus of the Subaru telescope, which gives us a superb image quality. And this is really important for us because we are very interested in the shape of the galaxies. So in this sense, HSC is one of the best weak ranging machines in the world. So using this instrument, we carried out Subaru strategic program, SSP survey. SSP survey have the 3 layers, and one of which called the wide layer is designed for the weak ranging cosmology. And it is shown on the red footprint. And it has overlap with other external major survey like SDSS or ACT or Viking, etc. So we can potentially perform joint analysis combining this HSC data and this major external data set. And the observation of the HSC is completed in 2021, but we will mainly focus on the HSC year 3 data set, which is taken until April 2019, and which covers roughly 400 square degrees. So for now, using this HSC year 3 dataset, we have published 9 papers, and especially we are going to focus on this project for the challenges in photometric latitude calibration and cosmic shear cosmology analysis, and 3x3 point analysis, and the last one is the very latest result of the cluster cosmology. So now it's time to jump into the challenges in the photometric latitude calibration.
Thank you so much, Sunao, and thank you for the organizers to giving us the opportunity to present our work here. I'm Markus Rau. I'm a postdoc at Argonne National Laboratory, and I will very briefly talk about the calibration of photometric redshifts, which is a very vital part of our analysis. Sorry. All right. To give you a little bit of an overview, so now already mentioned that our cosmological analysis is based on the analysis of two-point functions. Now, these two-point functions that we use in optical surveys like HSC view the density field in projection along the line of sight. So we need to reconstruct the distribution, the redshift distribution of samples of galaxies, and that is really the primary interest for our analysis regarding photometric redshifts. So, we need to estimate the redshift of the HSC Y3 source catalog that we use for this analysis using this broadband optical photometry. And the optical filters that HSC is using are shown here on the right-hand side, GRICY. So what you can see is that we need to infer the redshift information of galaxies using this broadband filter information. We performed 3 analysis to come up with a reconstruction of this sample redshift distribution. The first one really deals with how to reconstruct redshifts of individual galaxies using a variety of techniques, including template fitting and SPS modeling, and also empirical techniques that utilize training data. The main focus of this talk will be the second paper on the redshift distribution inference. So how to reconstruct the sample redshift distribution, the redshift distribution of the sample of galaxies using the information from the redshift information from the individual galaxies. And the third component in this chain is the development of statistical techniques to marginalize over the photometric redshift uncertainty. And that is work done by Zhang et al. We'll very briefly go through our results and what are the basic principles that we use to reconstruct the sample redshift distribution. We first of all discuss in our work a variety of quality cuts and sample selection techniques to remove galaxies that have outlier populations that extend towards very high redshift, so beyond redshift of 2.0. The redshift range higher than 1.2 is a problem for us because a central component of our redshift calibration is the usage of cross-correlation techniques, where we cross-correlate our source sample with an LRG sample extracted using the Camera code. And we don't have LRGs, very complete LRG samples higher than 1.2. So we cannot really use this calibration technique that we use to check and infer our redshift higher than 1.2. So everything that's beyond 1.2 has to be taken with a grain of salt, and we use a quite conservative approach. In general, our redshift inference is based on 2 sources of information. The first, as I mentioned, are cross-correlations with the Camera LRG sample. And we have information available here at a redshift lower than 1.2. And on the right-hand side, what you see here on the x-axis is redshift. On the y-axis is the probability density of the sample redshift distribution reconstructed. And the black points show exactly this information that we can extract from cross-correlations with the LRG sample. And the second source of information is, of course, the redshift information that we can extract using the photometry, and that is shown here in these gray bands. The combination of both of these informations is shown in the red band, and this will be used as our final analysis data product in the 3x2 analysis. So I would like to reiterate, everything that is beyond 1.2, we use a conservative assessment of redshift error. Everything that's lower than 1.2, we use this combination of the cross-correlation and the information that we have based on photometry. And we remove galaxies with very severe outlier populations because, as you see, due to the limited range of redshift calibration up to 1.2, we would not be able to really calibrate these outlier populations sufficiently. So this concludes my very short assessment of redshift calibration. I would like to refer to the papers, and any questions that you have can also be put into the Q&A, and I'm very happy to answer all questions that you have.
Thank you, Marcus. So thank you for having me here. So I'm Xiangzhou Li, a postdoc at Carnegie Mellon University. And so as mentioned, we measure the shapes, galaxy shape from the HSC image. So thanks to the good seeing of the HSC image, so our ship catalog our ship catalog is the deepest among all the other ongoing reclassing survey, and so we detect and select like 25 million galaxy, and the figure on the right, it shows the footprint of the HSC year 3 survey. And the figure on the left, it shows the comparison between other ongoing stage 3 surveys. And so I wish to briefly mention how we calibrate the shear measurement with our image simulation. So basically we use we distort the galaxy and include them and convolve them with the PSF, and to make the image simulation which representative to the HSC image. So we're using the image, the high resolution image from the Hubble Space Telescope, and we downgrade this space-based telescope, and we by convolving it with the HSC like PSF, and we add the noise HSC like noise to the image. And so in the finger on the downside, it shows the comparison between the our simulated sample and the observed sample in our real observation. So and our simulation is like the difference between the simulated sample and the observed sample is smaller than 1%. And so since we directly use the downgrade the whole the HST image, our image simulation include the blending effect. And after that, we model and calibrate the shear calibration, the shear measurement bias as function of the signal to noise ratio and the resolution, which is shown in the figure in the left-hand side. In addition to this, we also test for the case that if like two galaxies, like different galaxies are at different redshift, so they have different shear distortion on those two blended galaxies, and we find that as shown in the figure on the right-hand side, the bias is within 1%, and bias is dependent on the seeing size because of the good seeing size of the HSC. So the bias is below our requirement, which is below 1%. And yeah, after that, I'm going to briefly introduce the cosmic shear cosmology analysis. So the cosmic shear cosmology analysis is conducted in both real space and Fourier space. Basically, we measure the two-point correlation function in both real space and Fourier space. And I'm in charge of I'm leading the real space analysis, and another student, Ruhi Dalla, from Princeton University, she is in charge of the Fourier space analysis. So as you know, there are two ways to measure the two-point correlation function. One is to directly measure the two-point correlation function by cross-correlating the shapes in the real space, and another way is to to create a shear map and then transform to Fourier space and to calculate the second order correlation, which is called the Fourier space analysis. And since the two analyses are sensitive to different scales and also sensitive to different systematics, so they provide complementary information, and it's a good systematic test. So the two analyses are conducted in the blinded manner. So we are using two different sets of blinded catalogs. So we do not know like what is the true result among each other. So this slide briefly summarizes the measurement of the two-point correlation function in the real space. So the two components of the two-point correlation function. One is like the tangential correlation. Another is the correlation like between at 45 degrees. So which is shown in the figure in the upper part, and we also we measure the covariance of this measurement using like using 1400 ray tracing simulations, more catalogs, and we also so this plot shows this slide shows the measurement in Fourier space. So we got a really high signal to noise ratio, which is 26.4, and the figure on the right hand side, it shows the covariance matrix, which is also estimated from the same ray tracing simulation. And this slide summarizes our analysis framework. We conduct the Bayesian analysis. Basically, we model our data vector with including both the cosmology and the astrophysical effect, and also the systematics in the data. The astrophysical effect includes the bionic feedback and also the intrinsic alignment, and the systematics in fact include the systematics from the point spread function and the redshift distribution uncertainty, and also the shear calibration biases. So we're using the Cosmosis to do the analysis, and we're using the nested sampling algorithm, which is called polycode, to do the sampling. And the figure on the left hand side, it shows the summary of the 23 parameters we're using in our analysis. And we have like two different kind of a prior. One is a flat prior, and the other is the Gaussian prior. I need to mention that, so since we do not, as Marcus mentioned, since we do not have the calibration sample for clustering redshift estimation for the beyond the redshift 1.2, which is for the last two redshift beams. Therefore, we apply a really conservative flat prior on the last two redshift beams, and as shown in the figure on the right, so the solid line shows the NZ estimated from the clustering redshift and the photometric redshift, and the dashed line shows the posterior of the updated NZ estimation, which is from the cosmology constraint. And okay, this is the report of the final constraint and the comparison between the two different analyses. So we find that our two analyses we are consistent. This is after unblinding. We find the results are consistent with each other. And we also did a lot of systematic tests, for example, tests for different modeling setup, and also different, like we also conduct the internal consistency test, which is shown in the right figure. including separate the data into different subfields and use different photometric redshift estimation and also the remove one of the redshift bins and also different scale cut, and we find the results are stable with all of this analysis choice and also the different internal setup. Okay, this is the comparison between our analysis and the cosmic shade analysis from other surveys, including the DES and KIDS, and also the comparison between the Planck cosmology analysis. We find that our result is consistent with the other weak lensing survey, but it's like about 2 sigma. The S8 estimation is about 2 sigma lower than Planck. And then I will pass to Sunal for the 3-cos 2-point analysis.
Thanks, Shanchon. So hello again. So I'm Sunal Sugiyama. So I will talk about 3-cross 2-point analysis, which is a joint analysis of the HSC weak lensing data and SDSS spectrum data. So here is the footprint of the HSC shown in blue and the SDSS spec data shown in red, orange. And we want to make a cross correlation between foreground lens galaxy taken from the SDSS and the background HSC weak lens galaxy. So we selected HSC galaxy, which is beyond lens redshift of within the SDSS galaxy, which is after the redshift distribution after selection. So sample selection is shown in the bottom panel. And we see that there's a completely nice separation between the foreground lens galaxy and the background HSC shaped galaxies. So using this sample, we measured 3 different 2-point correlation functions. First one is galaxy clustering, which is autocorrelation of the position of the SDSS lens galaxies, which is the measured signal is shown in the middle top panel. And second of the bubble is the so-called galaxy-galaxy ranging, which is a cross correlation of the position and the shape, position of the taken from the SDSS and the shape taken from the HSC sample. And the last one is cosmic shear, which is the autocorrelation of shape and shape. We combine these 3 different kinds of 2-point correlation function to constrain the cosmological parameter. So interesting point is of this 3-cross 2-point analysis is that we can break the degeneracy of the cosmological parameter and the galaxy bias parameter. So galaxy bias is the relation between the galaxy density field and the underlying matter density field. So basically from the observation of the galaxy itself, we cannot constrain the underlying matter density field itself. So what we observe is really a galaxy density field itself. So, and there is a complete degeneracy between this galaxy bias P and the cosmological parameter. We needed to break the degeneracy of this galaxy bias and the cosmological parameter. And this degeneracy can be broken because the dependence of this probe on the galaxy bias parameter is different for these different probes. So we can, by combining these 3 different kinds of 2-point correlation function, we can break the degeneracy. And here is a demonstration of how the cosmological parameter degeneracy is broken. And by combining, for example, the galaxy clustering and the galaxy ranging, I mean the WP and the delta sigma, we can put in a meaningful constraint on the sigmoid and the omega matter, which is shown in orange line. And also by adding the information of the cosmic shear, which gives a 3-cross 2-point analysis, and we can get more tighter cosmological constraint, as shown in the blue contour. And using this technique, we constrain the cosmological parameter. But before that, we validated this strategy because there's a so-called uncertainty of the galaxy halo connection. And also, there's also another uncertainty like the baryonic feedback on the cosmic shear data set, and also the observational uncertainty like the photo-Z bias and or PSF systematics. We needed to validate our methodology is valid to these uncertainties. So to validate our analysis method itself, we first generated mock signals using artificially adding these uncertainty and apply our parameter inference pipeline to these simulated data and get the cosmological parameter constraint, and by comparing the input and output cosmological parameter, we can validate the analysis itself, method itself. And the result is shown in the on the right panel. And you can see that S8 parameter is pretty robust against these various kind of the uncertainty. And especially this law is focusing on how our analysis method is valid against photometric relationship uncertainty. So we, as Marcus and Shanton is already mentioned, so there's a limitation of the calibration of the photometric redshift, especially at the high redshift, greater than 1.2. So we also, in this 3x2 point, we also adopted a very conservative choice of prior. With this flat prior, it is shown in the second line. We can recover the input cosmological parameter, which is shown in vertical dashed line within 1 sigma error bar. So with this pipeline, we got cosmological parameter constraint as shown in the left panel. Here I'm showing the constraint on S8 parameter and as long with photometric redshift calibration. And basically what we got in the 5% constraint on the S8 parameter, and also we got non-zero photometric redshift calibration. So this finding of the photometric redshift calibration is consistent with what was found in the cosmic shear, tomography cosmic shear analysis led by Ruhi and Shancho. So this is more or less consistent with cosmic shear analysis. And after unblinding of our analysis, we compare our S8 constraint to the external dataset, like the DES and the KITS. And also we compared it to the Planck result. And we found again 2.5 sigma tension between HSC and a Planck result. Now we pass to Momi for her result.
Thank you, Sunao. Hi, I'm Tomomi Sunayama. I'm a postdoc at the University of Arizona, and I will present the optical cluster cosmology analysis using SDSS red mappa clusters and HSC Y3 lensing measurement. So clusters can constrain cosmological parameters by just counting the number of clusters. This is because the number of clusters corresponds to the tail of halo mass functions, which is sensitive to the cosmological parameters. And clusters are considered to be statistically competitive with other cosmological probes if cluster mass can be accurately measured. However, because cluster mass is not a direct observable, we need to assume mass observable relation. And this is the biggest uncertainty in cluster cosmology. Optical cluster sample is relatively complete up to low mass clusters and also susceptible to many systematics. This is from the DSY1 cluster cosmology result, which is shown in the dashed line and gray contours. And the S8 value from the DSY1 cluster analysis was lower than any other late-time probes. And we were quite puzzled what caused this low S8. And I and my collaborators found that the problem is on the projection effect, which is considered to be one of the biggest systematics in cluster cosmology. So the projection effect is a misidentification of member galaxies along line of sight, which alters the mass richness relations. So basically what's happening is that when you are identifying like clusters from imaging data, we have image of red galaxies and try to find the overdense regions. But because the line of sight distance uncertainty is large, we often include interlopers along the line of sight. So what basically do is that cluster finder preferentially identify clusters on aligned filament along the line of sight. And this preferential selection of aligned structure cause a boost on clustering and lensing. So here in the middle panel, I'm showing the comparison between observed cluster with projection effect and true clusters which doesn't have projection effect. And this 2D clustering ratio basically shows that observed cluster with projection effect are more isotropically distributed with respect to the true clusters. And this causes a boost on lensing signals, which is shown in the right figure, where I took the lensing signal ratio between observed cluster and true clusters. And on large scales, you see that boost for all the clusters. And this is because of this anisotropic distribution of observed clusters. So one of the things that we did in our paper is that modeling projection effect on clustering and lensing, which is shown in the blue line, which we call measurement, which has a projection effect boost on large scales. And prediction means that this is a prediction from the halo mass functions, which assumes the isotropic distribution of the clusters. And what we need to do is trying to model this blue line using this orange line. For this, we use like 3 parameters which are circled, and this pi naught basically takes care of the boost on large scales, and R naught takes care of the transition from the one halo term to halo term, and this C takes care of the decrease on large scale. So modeling projection effect is crucial because if you don't model this projection boost on lensing and clustering amplitude, you get bias omega matter and sigma 8, which is shown as the green contour. So basically, without projection effect modeling, you get lower omega matter and high sigma 8. Another thing that we changed from like traditional cluster cosmology analysis is that instead of using backward modeling, we decide to use full forward modeling, where from the theory side, we set the cosmological parameters, which gives halo mass functions and clustering and lensing signal. And on top of these predictions, we model the mass richness relation, projection effect, and miscentering and photometric redshift error, which gives a theoretically predicted abundance, lensing, and clustering. And we compare these to the measured abundance, cluster, and lensing to do the analysis. And the advantage of this way is that from the cluster lensing, from one halo term, we can get the mass richness relationship, but also we can measure cluster bias from the large scale, which is a function of the cluster mass. So in addition to mass richness relation, we also get mass information from the large scale, which gives a better precision to constrain the cosmological parameters. So with this method, we apply to SDSS red mappa cluster samples, which covers roughly 8,300 square degree from redshift of 0.1 to 0.33 in the richness bins, in the 4 richness bins, which in total like roughly 8,000 clusters. From this sample, we measure cluster abundance and cluster clustering. And by using HSC Y3 shape catalog, we measure the cluster lensing. And this is a result from the cluster optical cluster cosmology analysis from red mappa clusters and HSCY3, where our S8 value is 0.816, and it's consistent with other CMB and large-scale structure cosmology probes within 1 sigma. So now I think we are now at the summary.
Yeah. Yeah, I think we can now take a question.
All right. So one question that will be answered live is someone asking, how do you blind your data? What's your blinding strategy? If you want to touch back on that.
Yeah, that's a good question. Yeah. So here is how we blinded ourselves during the cosmology analysis. So we have the 2 stages of the blinding. So one is a catalog level blinding. So in which we prepare a 3 blind catalog, and one of which is a true shape catalog, but the 2 which is kind of a fake catalog, in which the amplitude of the galaxy shape is have an offset, slight offset. So due to this offset, the inferred cosmological parameter from each of these 3 blind catalog is shifted as a result of the shift, fake catalog. So for example, and this shift in a blind catalog, I mean the shift in amplitude of the galaxy shape is designed to have a roughly 0.1 sigma, and which is larger than current observed tension. So to design to have this shift as large as this size, we can avoid the confirmation bias to preferentially conclude that comparing our result to the existing CMB or Planck or other external data. And the second stage of the blinding is analysis level of blinding. And if maybe every time we make this kind of the cosmological parameter constraint plot, we always shift the central value of the cosmological parameter to 0. By doing that, we can avoid direct comparison of our HSC result to the external data set. So this is the way we blind our analysis itself. And also, let me add one thing. And also, during this blind analysis, we also perform any kinds of systematic tests during this blind analysis. And after we satisfy these systematic tests, we can unblind. And after unblinding, we promise that we never change our result. So this is a strategy to protect our result from the confirmation bias. Thank you.
Are there any more questions that anyone has for our HSC speakers? Looking at the Q&A. Don't be shy. Well, then I guess that means you did a terrific job explaining the status of HSC. Giving it a little bit more time.
If time permits, Marcus, do you want to add something about photo decalibration? Because you didn't have much time for presenting your analysis, perhaps.
No, I think I covered the basics. I think I'm very excited about the future surveys that are coming up now, especially DESI. That's something that will, I think, very much improve our capabilities to calibrate faint galaxy samples. So that's one of the extensions that we plan specifically in the area of photometric redshift calibration, to look at calibrating these higher redshift distributions better with DESI. And I think from a methodological point of view, it's quite an exciting problem, because you also have to account, for example, for this degeneracy with galaxy dark matter bias. So it's not only, a methodological aspect that you have to go through to get to cosmology, but it also has a lot of, I think, interesting aspects from the astrophysical side. So stay tuned for that. So there are two, I think, there are two questions.
We'll take them in order. So, oh, maybe you were talking about photoses. So did you use morphological information for photoses?
So I think what you're answering is, so you can use morphological information in several ways in terms of photoses. I'm just trying to extrapolate a little bit what the question addresses. So we have a very simplistic galaxy dark matter bias model, so that's where you could use morphological information in the sense of getting a good galaxy dark matter bias model. So there we so for each tomographic redshift bin, we assume a parameter, a constant redshift independent parameter for galaxy dark matter bias in our source sample. So that's something where we don't use morphological information. The reason for that is really because the error bars are still quite high. So using a very complex galaxy dark matter bias model wasn't something that was very much supported by the data. But if we go forward in DESI, this will definitely be something that we will be looking at. In terms of the redshift estimation of individual galaxies, you could use morphological information. Of course, the template fitting methods, they do, of course, they construct templates for different galaxy types. So that's where morphological information or modeling is done. I think that's roughly what we use in this field. Yeah, because we have to. So we don't have external morphological information. We only have photometry, and every morphological assessment we do is part of our modeling. Yeah. If that answers the question, I mean, I'm not sure if I did a good job there.
I'm sure there can be a follow-up if something wasn't clear. Yeah. In the meantime, let me ask the next question, which is, what are future observing and analysis plans and schedules as far as you are concerned? I think maybe Tomomi can answer this.
Sorry, for the optical cluster specific or like in general?
I think probably both, because knowing what data are coming in is of interest, I think, to most people.
Mm-hmm. I think in general, like I will probably repeat the same thing that Marcus said, like having like DESI or spectroscopic data will improve the photosy uncertainty calibrations, which is the biggest uncertainty for any like weak lensing analysis. For optical clusters in general, like now, like I'm interested in moving to using HSC cluster catalog, which goes up to redshift 1.2, and it gives like tomographic informations which can constrain omega matter better. Also, another way is more exploring different data sets between photometric data and spectroscopic data. In particular, BAO measurement from spectroscopic survey will really break the degeneracy between omega matter and sigma 8. So I think those things are very exciting for future.
All right. Thank you.